Well, thanks for the introduction, Ross. Yeah, so obviously I'm Donald. So today I'm going to present Wasmtime, which I've developed along with Arjun and Yuri, my advisors. And Wasmtime, it's an extension to WebAssembly, which adds support for delimited continuations. So for the structure of this talk, I'm going to start the talk with two sections in which I'll introduce WebAssembly for people who aren't familiar, which probably isn't too many in this group, but that's fine. And I want to do that with a view of how to compile C to WebAssembly in a straightforward way. And then I'll introduce the difficulties that come up when you try to compile Go to WebAssembly. And then after that, we'll dive into the Wasmtime system, which fixes these problems. Okay. So to start with, I want to give a brief introduction of compiling C to WebAssembly, which after that is then typically run in a runtime such as like Wasmtime in a sort of JIT style. But to start with the compilation from C to WebAssembly, I want to start by running through like the basic features of C and seeing how those map to WebAssembly. And let's start with expressions. This is the easiest. So WebAssembly is a stack machine. So all we have to do is just sort of recursively compile the left and the right operands of each operator. So here we start with a multiplication. That's going to turn into a I32 mul operator in Wasm, right? And then we compile the left and right operands recursively. So the 2 will become an I32 const. And then the left operand, the 5 plus 3, that'll compile to an add and a 5 and 3 const. Okay. Right, and then pretty unsurprisingly, at runtime, the WebAssembly formal semantics, what they will do is they will evaluate this stack sort of bit by bit and reduce it until you get a value. And the other sort of detail here is that the WebAssembly type checking, it assigns a type to each of these instructions, and then the type checker can sort of check that the types throughout the whole stack are consistent. Okay. So expressions are pretty easy. Let's see, how do you compile functions? So functions are maybe even easier because they really have just a direct analog in WebAssembly. So let's start with the C function here, f, and it has a parameter s and its local variable y, and then it calls g. So WebAssembly has support for functions, which can take parameters and have locals, and they can return results. Right. And then WebAssembly also provides these special instructions to manipulate the local variables and like call functions and stuff. So here, to get the value out of x, you would do local.getx, and then you can mutate the local for y by doing a set instruction, and then you can retrieve it again to push it onto the formal stack, and then you can do the function call. Okay. Cool. And then the last feature, which is like really, again, straightforward to compile from C to Wasm is malloc, like things that you want in the heap. So let's say that we're mallocing some number of bytes. We get them into this pointer p, and then we do a write to this pointer. So the key thing is that like you can't put these 1024 bytes into the Wasm formal stack because you can't do any sort of like indirect read or write operations like arbitrarily into the Wasm stack. Instead, you have to use the linear memory feature of WebAssembly, right? And linear memory is just this huge chunk of byte addressable memory, which is bound checked, and you can just sort of do whatever you want with it, including implementing a memory allocator like malloc, which you can implement that easily to just like return an index into this linear memory table, right? And then after that, WebAssembly gives you like store and load instructions to read and write from that table. Okay. So we sort of have this correspondence of expressions. You compile to these stack operations, locals turn into locals, function calls turn into function calls, and mallocing stuff. This is done via stuff in linear memory. And then these things in WebAssembly are then going to typically be compiled in like a JIT fashion to x86 machine code in Wasmtime, for example, right? And the detail to keep in mind here is that yes, the formal stack in Wasm, it's sort of a virtual stack in the sense that it acts like a stack semantically, but some things on the stack will actually be allocated into like machine registers. And same thing for locals. Some of the locals will be allocated into registers. And of course, some things will also have to be spilled into the machine stack. And of course, function calls are translated to building up a call stack in CSS. And linear memory is just this separate region of memory. Okay. So that's fine, except I sort of lied. There's one wrinkle, and it's sort of an interesting wrinkle that's quite relevant to this. So in C, you can also have pointers not only to like malloc things, but pointers to local variables in the C stack. So let's say we have an int s, and we call g with some with the address of s, right? Now g could then do a write or read from that address. And just like we couldn't put malloc things into the stack, for the same reason we can't compile this by putting s sort of into the WebAssembly formal stack, because there's no way to like take an address and then do like an indirect write to that address later on. So instead, to compile this to WebAssembly, the technique is to build what I sort of call a shadow stack in linear memory. And the shadow stack is something that sort of WebAssembly is blind to, but the C compiler knows about, and the C compiler will treat it like a stack. So in this code, when you want to allocate s onto the shadow stack, you would have to emit WebAssembly code, which would like push something onto the stack, for s, and then pass that pointer to g, right? And then in the epilogue of the function, it would pop the shadow stack. Okay. So I guess in this sort of overview picture, the idea is that most of the time locals in C will be translated to locals in WebAssembly. But like sometimes when you're taking a pointer to a local variable and doing things with it, then you will have to compile this local to actually be placed into linear memory in WebAssembly. Okay. So that's C. But let's move instead to looking at Go, and let's see what happens here. So let's start with just this really basic Go code and sort of like walk through an attempt at compiling it. So okay, we define we set s to 0, then we do an infinite loop. The infinite loop is going to increment s each time, and then call f of s. Okay, so if we sort of take the C strategy of just doing this very simple compilation strategy, we could do this. To compile this first line here, we could like get the value of s, push 1 onto the stack, do an add, and then update s. Okay? And then to compile the second line, the function call, we can just get s off of the stack, or get s, the value of s, and put it onto the formal stack, and then call f. Okay. This would be right, except for the problem that in Go, every single time you're doing a function call, that is going to potentially trigger a green thread switch. Okay. So this code will not work. Why? Because this means that while f is running, f will potentially want to actually switch to a whole new thread, which means that f needs to somehow be able to switch to a whole new stack. You need some way to switch to a whole new stack. And moreover, you need some way to save the value of s somewhere before you switch to the new stack, so that you don't forget the value of s here. Okay, so instead, the technique is to use the shadow stack idea again. So at a sort of high level idea, the point is that what we need to do now is before we call f, we need to actually save s into the shadow stack, and then we can do the function call. And then after that, we can like pop the shadow stack. Okay, and in effect, what we're doing is we're taking the entire WebAssembly call stack, and we're mirroring it into the shadow stack in linear memory. Okay. So the picture looks like this, and that, okay, yeah, we still have to use a formal stack for doing like temporary computations, and likewise for the locals. But we have to make sure that in Go, before we call another function, we need to make sure that the call stack and all the locals and expressions that we need all get saved and sort of like mirrored into linear memory, into the shadow stack in linear memory, right? And then when we actually want to switch to a different thread, essentially the idea is to just update the sort of shadow stack pointer to point to a different shadow stack in linear memory. And the comparison with C is useful to think about. So in C, the only variables that need to be placed into the shadow stack in C are those that you are actually taking pointers to. All the other variables, you don't need to put them into linear memory. It's also a local analysis in the sense that one function does not affect any other functions in C, right? But in Go, you have to put essentially every single local variable into the shadow stack in linear memory prior to doing function calls, like up to maybe some possible liveness analysis, right? But it means that in a sense, you can think of it as you're defeating the sort of register-based calling convention of the Wasm runtime, because you're putting everything into the stack instead of some things into registers when you call functions. Okay, so I mean, I can pause if anyone has questions there, but otherwise I'll carry on.
Are there any questions from it?
Yeah, so the sort of like one sentence way to say the problem is that Go needs a way to manipulate the stack to switch threads, right? But WebAssembly just does not have any mechanism to do this, right? And you need, if you have a mechanism, it has to be safe, which is perhaps why it doesn't have it. It's somewhat challenging. So to address this problem, our strategy is to take WebAssembly here and extend it to Wasm which is just WebAssembly, but we add in a handful of these stack manipulation instructions. And when you use these instructions, they will then manipulate the formal stack on your behalf. And then to sort of, for two reasons. A, we want to sort of evaluate that Wasm is actually a like viable, good target for languages to compile to. And B, we want to write code examples in like C instead of in WebAssembly directly. So we introduced this language CK, which is C, but also extended with stack manipulation functions. And we show that you can compile CK in a very straightforward way to Wasm, just as we compiled C in a straightforward way to Wasm. Okay, and sort of from here, after this, I want to show my examples actually in CK using the stack manipulation functions in CK, which we can sort of list out those functions and instructions here. And then after that, I'll switch back to WebAssembly to give the formal semantics of Wasm. But for the intuition, for looking at examples, these functions in CK that we've added, like very, 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 very closely mirror the semantics of the Wasm instructions. So it's worth looking at the C for the intuition. Yeah. So after this, so I have 3 code examples. So code examples can be somewhat confusing. So feel free to like interrupt during examples to talk it through. So the first example to go through is I guess maybe the most salient one, which is building a green threading library using CK. So on the right, let's start on the right. We have the client code on the right, and it has a main function which like creates 2 threads on this like thread main function, and then joins. Okay, I'm not going to show the thread create and join code in this slide. It's in the paper, but let's focus on how this yield works. Okay, so this thread function, it just printed A, and then it calls thread yield. How does that work? So thread yield is this function down here. And what thread yield will do is it will call this new control function, which is a like new primitive in CK. And what control does, excuse me, what control does is it will call the function that you put in here. So it will call yield handler. And for the first argument to yield handler, it will pass the captured continuation, which, as you note, the type is a like integer. So it will actually pass like a unique like ID of the captured continuation. And it will run this function here in a brand new stack. So in effect, it's A, capturing the current stack, switching to a brand new stack, and then running this handler function with having passed an ID referring to the captured stack as the argument. Okay, and then what does this handler do? So with this K is essentially representing the stack that was just captured. And what is that stack? It is the stack of the thread that was just running, that you are trying to yield from. Okay, so with this K, we just insert it into the queue on the first line. And then after that, we do this restore function. And the restore is like the opposite of control. So we dequeue something from our thread queue. And the thing that we are going to dequeue is a different ID for a different saved continuation. So we dequeue that, and then we restore to that other ID. And when we restore, then we will just discard this brand new stack that the yield handler was executing in, and then we will switch back to the thread stack that we're restoring. Okay. Actually, does anyone have questions about this example before I jump to the next one? Okay. Right.
What are the zeros in control and restore mean?
Exactly. Good question. So so when you put the 0 here, that will sort of just be passed through as the argument to the function here. It's just sort of like passed through directly. So whatever you put there will come out there. And likewise, when you do restore, whatever you put here will then sort of be the return value of the control function, which was where you captured the continuation. So we don't use it for threads, but for other examples, especially this argument parameter for the that you give to the control here, you like use this to like pass through the environments that you would typically build up after doing closure conversion.
So the first argument to restore is this stack ID, effectively.
Yes, it is the stack ID that you're trying to restore. The second argument is the value that you're going to sort of insert into the hole in the stack that you left.
Okay, thanks.
If that makes sense.
Yep.
Yeah. Yeah, and neither of them are useful for green threads. Okay.
May I ask why you did that?
Which one?
I mean, you're basically putting values in two different places.
Right, so they serve different purposes. So the value that you give to the restore, that is really actually very, very similar to like call CC or something in Scheme, in the sense that when you're restoring something in Scheme, what is it? You have a functionalized version of the continuation, you call it with an argument. Right. This 0 in the restore is that argument. Okay.
Oh, okay, I see. Okay.
So that's not different. The different thing that we have here that you don't see in Scheme is this argument to the control, right? And we do that to sort of enable you to sort of pass through these environments which you would normally get through closure conversion, right? And you need that here because you don't have like higher order functions like you would in Scheme. That's a little bit more clear in the second example. Right. So the second example is a generator example. So let's start with the code on the right, which is sort of the client code. So so in the main function, we call this like make generator function, which I'm not showing the source code for that right now. And you pass this function pointer to this example generator function. Okay. And this example generator function, what it does is it just does an infinite loop, and it does the generator yield each time. So it's going to sort of yield the values 0, 1, 2, 3, 4, 5, blah, 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 blah. Okay. And then in the main function, we then loop just 10 times, and we grab the next thing from the generator and print it out. And then at the end, we free the generator. Okay. So this thing is a little bit of a chicken and the egg in that it's sort of hard to sort of show how it gets started. But let's sort of say that this has already been running for a few iterations, maybe. And let's say that what's happening right now is that, okay, we've called genNext, and and the generator is currently running right now. And what it does is on the next iteration of the loop, it hits the gen yield function. So let's walk through how the gen yield function will then work after that. And we pass two arguments. We pass the value that we want to yield back to the main body, and we also pass the generator. Okay. And we call this, so this gen yield function, right? It's going to just quickly save away this value into the generator struct. Okay. And then it's going to capture the current continuation. So that means it's capturing the stack of the generator function, right? And it's going to call this yield handler. And here's where we're using the argument here. We're putting G in for the argument in the second argument of control. So that will just be passed through directly to the yield handler function. It's a little bit unclear, but like how did I actually drive this code? I literally just started with doing this example in Scheme with call CC and just literally doing closure conversion by hand. And then you actually will get this form. Right. And then this K here is now the captured continuation of the generator function, right? And we save that into the struct, so save it away. And then we restore to the continuation which we had previously captured when we did the genNext function call. And what do we restore back with? We restore back and we pass this value back, which will then end up being the return value of this generator of the genNext call here. So yeah, this one is a little bit hard to think about because it's sort of chicken and egg. But if you're interested, I would suggest like looking at maybe at the full example in the paper that has all of the code. And the other interesting thing that happens here is let's think about what happens when this for loop finishes running. Okay, so on the last iteration, we call genNext. Okay, then the generator runs. It calls yield. Okay, when it calls its yield, it's going to capture its continuation and save it. Okay, and then return back here. Then this loop terminates, and then we free the generator. Okay, but don't forget the gen yield, when it did that the last time, it actually saved its continuation, but we're actually never going to use it because we're done with the generator. So therefore, when we free the generator here, we also need to actually explicitly delete that continuation that was left over. Otherwise, we're essentially leaking the stack. So this is something that comes up, which is sort of weird, right? But it comes up naturally in this example. You don't need this in Scheme, right? Because it's garbage collected. But it sort of comes up in a natural way here. Okay. So the last example is sort of the most fun one, which is this like probabilistic programming example. So I haven't said this explicitly, but we'll do that in the semantics in a moment. But the design of Wasm is one-shot continuation. So when you restore a continuation, it then marks that continuation as used up. You can't restore to it again. But then we also support a like explicit continuation copy instruction, which is the point of this example. So if we start here on the right, this is essentially giving you like an embedded DSL and in C++ for doing probabilistic programming. So we have this sum dsits function, which we run sort of inside this like driver function call in main. Okay, and this sum dsits function, okay, it makes this vector of just 1, 2, 3, 4, 5 sits. And then it calls uniform dsits plus uniform dsits. Okay, and what this will end up doing is it will actually, for you, it will compute the full probability distribution of this expression. So how does it do that? So let's start with the uniform function. How does that work? So the uniform function, it starts down here. Okay, its argument is just this vector of numbers that you're uniformly sampling from. And what it will do is it will capture the current continuation and call the uniform handler function here. Okay, so what does uniform handler do? So uniform handler has received in its argument k the capture continuation, which in this case the capture continuation will be, after you get the return value here, then it will add and then call uniform again. Right, this is the continuation. So it will take this continuation k. It's going to loop through the arguments except for the first one. So it's going to loop through 2, 3, 4, 5, and 6. For each of those, it will copy the continuation and save it along with the value, 2, 3, 4, 5, and 6. It will save all of that into a continuation thunk and sort of just push this thunk into this vector up here. Okay, and then for the first thing in the list of arguments, which is 1 here, for the first thing, it will then just immediately return back by restoring the continuation. So, excuse me. So on the first, so immediately it will return back with 1, right? And then it will do uniform dsits the second time, which will again immediately return back with 1. So then this whole thing will return 2. Okay. And what happens after it returns 2? Well, you have to look at this driver function, which call it. So driver will execute it here, execute sum dsits here, save its return value, and then it will check if there are any more thunks left to evaluate. Well, while we were doing these evaluations, we pushed a whole bunch of thunks into the vector. So we'll pop those off and restore to those. So that means that you're effectively going to generate all the combinations where you have 1 and 1 sample at end, 1 and 2 sample at end, 1 and 3 sample at end, and so on. Okay. Does this example make sense to people, hopefully? Okay, so so that sort of concludes the examples. So next I'll go through the formal semantics of Wasm-K. So I'll start with control and restore. So on the top we have the semantics for control.
Question first. So that was all in the CK, right?
Yes. So this was all CK, and semantically is like very similar to Wasm-K, and that's why I want to do the Wasm-K semantics now.
The question I had was, I'm guessing there's a slight difference, which is that you talked about how C needs to have these shadow maps or shadow stack. So I'm guessing your continuation copy in C does also a copy of the shadow stack and then the Wasm instruction. Is that right?
Exactly. That's exactly
cool,
yep. I can talk more about that later, but exactly, yes. Okay, so now in Wasm-K, let's look at the semantics of control. So the top line is the reduction rule for control. So control, it's taking sort of this immediate argument, which is the function for the control handler, and then this v is just something that's on the stack, which will then be passed to the h function. Okay, so here, this is the evaluation context here, but we've sort of in our semantics, we've been careful to define it to make sure that it refers to the entire stack, not just sort of the local, not just the local evaluation context. Okay, and we start in with the state s here, and then we transition to this new state, this new store, excuse me, s prime. And what is S prime? Well, S prime is the same as S, but where you've saved your evaluation context. That is, you sort of save the whole stack except for this little hole here. You save that into S prime sort of at index K. Okay, and what is index K? Well, index K is just some new, fresh index into the continuation table that was chosen by the runtime. And what do you do with this index K? Then you make a brand new empty stack. So this whole huge stack here, we've blown it away. Now the only thing we have in the stack here on the right-hand side is just calling the function h with the continuation ID k and v as arguments. Okay. Oops, excuse me. Right. So now for the restore reduction, it's sort of the opposite. So in the restore case, you are giving restore the argument k on the stack, which is supposedly a continuation ID. And the current stack, the entire current stack, you discard. So this lmaps, it does not appear anywhere on the right-hand side. You just boom, throw it away. And this lmaps prime is the stack which was retrieved from the store S, like at index k. And we again update the store. And here, all that we do to update the store is we just sort of mark that index k in the table now as free because you have used it up. And note that the argument v, the value argument to the restore, it's being substituted into that hole in the stack, which was left. This hole was left when you did the control instruction originally. So a visualization is sort of easier to understand than the math maybe. So when you start in the situation where you are currently executing this active stack, I'll call it an active stack, okay? And suppose you then do a control instruction. So then the control instruction, it will take that stack, it will save it into the continuation table at some free index, maybe index 1 this time. And then it will switch to evaluating the new handler, the new function handler in a brand new stack, right? And then after that, let's say that we then do a restore instruction where we restore index 1, right? Then restore index 1, that will then take this stack here, boom, it'll put it back as the active stack, and it will free up the spot in the table. Okay. And then we have the continuation copy construction. And this one is actually easier because it doesn't actually change the current stack. So in this case, you just give the continuation ID as an argument to the continuation copy instruction. And all it will do is it will just copy that to a new place in the table and return for you the new index that it put it in at the table. So in this example, we're in some active stack right now, and we have some stack saved at index 1. If you then do a copy of index 1, then it'll choose some free spot on the table, maybe 3. It'll copy it from 1 to 3, and it would then return 3 back to you. And I won't walk through how continuation delete works because it's pretty self-explanatory at this point. It just removes it from the table. And then for all of these instructions, there's just a case that if you give it a free spot, so if you're trying to restore an index and that index actually is a free one, then it will just trap. Okay. Yeah. So what do we have so far? We have these 4 new instructions slash functions in CK and Wasm, which I've sort of shown by example and through semantics. We have control, restore, and then in copy and delete. I haven't yet shown prompt. Okay, so that's where we are so far. If people have questions about these ones so far, I can take that now, or I can move on.
I have a question.
Yeah.
Is it ever useful to be able to do integer arithmetic on that identifier k that refers to stack?
No. So like for like a finalized design, I mean, it's totally reasonable to like make it a distinct type. It was just sort of for expediency that, okay, then if you do that, you also would need, let's say you call it a new type like KID type.
Yep.
Right, then you just need to make sure that you do have like KID load, KID store, and then like local set and store instructions for that type. That's useful. I haven't seen cases where you actually want to do like integer arithmetic though.
Right. The idea is that the number you get back is pretty meaningless, right? It's just
yeah.
Sort of, okay.
Yeah.
And all this was done before, I think, the reference types proposal and before, I think, the exception handling proposal, right? So this is like very much original WebAssembly.
Yeah, this is all. Yeah, this is all sort of without trying to do this by interacting with these other proposals. Yeah.
Gotcha. Thanks.
Yep. Okay, so the main question to ask yourself now, though, like, is it safe? Because that's important. So the answer is almost. And we need to fix the almost part to make it definitely safe. But before I go into like why it isn't safe, let me give the very quick argument for why it is like really almost safe. Okay, so the quick argument there is that when you do a control operation, you're just taking the current stack. You're like you're sort of taking out this little hole, and what will that hole be? It will always have the shape of a single i64. Okay, and then you save this stack away somewhere. You switch to a new stack. Okay, and yes, you are switching stacks, which maybe is weird, but the point is you're still always like preserving the types of each of the stacks separately. And then when you do the restore, you have this stack which has a single hole for an i64. The only way you can restore back to it is by doing the restore function and substituting in a single i64. So you're never going to be able to take that stack and substitute in something of the wrong type or something. Okay. So that's sort of the sort of intuitive argument. But the issue is when you want to start doing FFI. That's when things get weird. Okay. So let's walk through this example because I think it's pretty interesting. So for those who don't know, like WebAssembly, it's typically executed in a environment where you have some like host language calling into WebAssembly. So on the web, it would be like JavaScript calling into WebAssembly. In Wasmtime, it would be you could have some Rust code which then calls into the like JITted WebAssembly code. Okay. So in this example, we have a foo Rust function and a like main Wasm function. So foo Rust just called main Wasm. And let's see what does main Wasm do. So first thing main Wasm does is it then calls another Rust function, bar Rust. And then let's say that bar Rust then calls this function bad Wasm. Okay. So all the yellow ones are the Wasm call frames, stack frame, excuse me. Okay. So what does bad Wasm do now? Well, it's going to do bad things based on its name at least. So first thing that I'm going to have bad Wasm do is do a control instruction. So that will capture this stack. It will sort of save it into the continuation table. Okay, and it will switch to this new active stack, which is, I don't know, some new function, right? And let's see, what does this active stack do? Well, something it could do is it could copy that captured stack. And that would potentially include the Rust stack frames. Okay, and then after this, it could restore this stack. So now it's going to restore here. Now we've jumped execution back to be inside the bad Wasm function. Let's say that then bad Wasm it returns. Now we're in the bar Rust function. Bar Rust will sort of finish executing now. You pop that off, and now we're back inside the main Wasm function. Okay. Let's say that the last thing that main Wasm does is it then does another restore instruction and restores that other copy, right, which now executes bad Wasm, which returns, you pop that off, and now what happens? now you're going to execute and sort of return from var rust a second time. Okay, so this means that the prologue of var rust will have been called once. The epilogue of var rust will have been called twice. And that's really bad for Rust, right? That's going to give you double free bugs in Rust. Okay, so that's very bad. Okay.
Donald, can I ask a question? So the doubling is definitely bad. What about the throwing away, like just not calling, because Rust is fi not.
That's going to be bad too, because at least in Rust, Rust will allocate memory in the prologue, right? And then in the epilogue of the function, based on scoping and typing stuff, is going to free the memory in the prologue. So if you can somehow skip var rust and return back to foo rust or something without running the var rust epilogue, you're going to leak.
Okay, cool. Thanks.
Yeah. Yep. Okay. So sort of our solution that we came up with is a somewhat strange sort of delimited continuations. And our intuition is that we want to add in sort of a type of delimiter at these FFI boundaries. We actually allow you to sort of use the prompt instruction wherever you want, but we enforce it implicitly at FFI boundaries to give you safety. And the intuition for how to do this here is that we're going to keep track here. In addition to having the continuation table, we'll also keep track of this little piece of data, which I'll call the root stack. And it's going to remember which stack sort of has these mixed language stack frames, in a sense. So
can you take a quick interrupt here? It seems to me that the argument that you've got here for FFI applies just as well to a mixture of C and Go, both compile to Wasm.
A mixture of C and Go, both compile to Wasm. Like if you compile C and Go and then you call each other from Wasm. Sure. Yes.
It's not really FFI in the sense of going out of Wasm.
Yeah, I suppose it's a problem in the sense that when you have some function like, in this case, Rust, you need to make sure that when you're going back into it, you're sort of maintaining the sort of stack discipline, right?
Yeah.
Yeah, so it's definitely a very good question how that works out when you're compiling two different languages to Wasm, right?
Right.
Yeah.
Or actually, even even if it was just Go, if you have a bad actor in Go, as it were, doing copies it's basically the copy that's dangerous here.
Yes. So so I suppose if you're compiling Go and C to Wasm, then sort of the worst that can happen is that you're going to sort of mess up your continuation tables in a sense inside of WebAssembly, but that's not going to expose sort of unsafety in the sense that it won't go outside of the WebAssembly runtime, right? The issue with the FFI is that you're going to be able to sort of leak these security problems to be outside of the runtime.
Interestingly, these issues will, except for not for copy, but for the throwaway, the issues will come up also from the exception handling proposal. Because the exception handling it doesn't unwind any C code or anything like that. It's just going to jump over it. So it's will not bother anymore. It's just a question for the community as to what we want to do with these kinds of problems.
Yeah.
To Ross's point, I would almost say that it'd be really great if Wasm had some way to indicate that stack frames from the embedder are going to be jumped so they can be cleaned up, because I know this is a problem with Go's duct tape library where you can embed JavaScript in Go, where it's a huge problem where where the host functions you learn in Go like can't call back into JavaScript, or you'll have these weird safety issues.
Yeah.
So
Yeah.
since Ross mentioned the exception handling proposal, I haven't looked into it in detail. Does it address this issue in some way at this time?
Don't think so. Thomas, do you have a sense?
Basically, don't throw into code you don't trust.
Well, no, the problem here is that it's your code calling into other code that's throwing, right? So don't call code you don't trust, because it might.
So if you call code you don't trust, and then you might want to do a catch-all on the boundary and prevent that code from throwing through you. Of course, that might mess up that code if it expected that to not be caught. So really, the problem with coordinating between these disjoint trust domains where they're not sort of ABI aware of each other is not a problem we're really attempting to solve right now.
Donald, we'll let you keep going.
Yeah. We're nearly at the end, so after this, we can definitely have a discussion more. Yeah, so I guess the intuition is we keep track of this root stack, which is remembering the sort of unique stack which has mixed language stack frames. And the other trick is that then when we do another call into FFI, right? When we cross this FFI boundary, we're sort of implicitly forcing a prompt instruction to run. And right, when you run a prompt instruction, what we actually do is we are actually keeping a stack of continuation tables and these root stack pointers. So this is now a stack, and we push on top of the stack a whole new continuation table and root stack pointer. And this new root stack pointer will also point to the currently active stack. Okay. And then if this active stack then does this control and captures this stack and puts it in here, well, why did it go into the table at the top? Because now all control and restore and copy operations, they will all refer to the table at the top of the stack of tables. There's like no way to talk to the tables further down in the stack. Okay. And then when we try to do a copy of this, like here, we will disallow it at runtime. Why? Because we had updated the root stack up here to point to this new stack. Sorry, we had updated the root stack to point to the stack which was captured into the table here. And we know now that you're trying to copy the root stack, which we ban just via like at runtime a trap instruction. Okay, so that sort of eliminates that. So instead, let's just sort of like walk through what happens if the function didn't try to do evil things. What if the function, instead of trying to copy it, after that it just tried to just do a restore. So next, let's suppose instead that it tried to restore this stack back to the active stack. It would do that, restoring the root stack pointer as well. And then when you finish the FFI, right, you're going to finish the prompt instruction. And then that will actually pop that continuation table off. And now you're back here again. So it's a bit of a, I don't know, strange sort of scheme that we've come up with. But sort of here's the full semantics of all of Wasm-K. So here we have the control rule, the restore rule, the continuation copy, continuation delete, and then prompt rules, along with some error cases for them. And then down here, all of this stuff down here is just simply how do you update the store and stuff each time you do one of these instructions. Okay, and I don't want to walk through all of it, but the point is that this includes all of the like manipulations of this like stack of tables and stuff to do the prompt correctly. And I'll quickly say that, yeah, we also have pencil and paper proofs of safety, of type safety, that is of preservation in progress theorems using the semantics, and you can check out those proofs in the full paper on archive. And yeah, so in the future, it would be like interesting to take semantics of like Rust, for example, and the semantics of Wasm and then like really formally prove that you have safety of both the Wasm and the Rust code, right? But in this work, we just sort of showed that you get type safety of WebAssembly, of Wasm, excuse me, which will then sort of imply that you're not going to be able to skip past Rust stack frames or execute them twice. Okay, so sort of for the last part, there's some implementation questions. So Ross asked this earlier. So what about how do you compile CK to Wasm? Right, so for the most part, it's really easy in the sense that it's like super local. Like I didn't actually hack on the actual mscripting compiler itself. I just sort of wrapped it using like hacks of like C macros and then doing regexes on the like outputted code from it. And that works. And that works because it's just a very local thing to compile each function to each instruction. But there's also the trick that, as Ross pointed out, you need to also capture and restore the C shadow stack that's in linear memory. Because Wasm can't possibly know about that. Right. And then how do we implement Wasm itself? So we implemented it as a fork of Wasmtime. Right now, it only works for x86. And we implement it by just implementing each instruction, like control, as a call to some like handwritten x86 assembly code, and that assembly code will then properly like save and restore the registers and stack and stuff. Which, you know, if you're familiar with how set jump and long jump works, it's fairly similar to those. And as I said earlier, control and restore, these give, in our design, they are like one-shot continuations. So you can't restore something multiple times unless you explicitly copy. So this means that we can have control and restore be like very fast because they don't actually require doing any like move. They don't actually have to move the stacks around in memory or copy stacks around in memory. There's just updating pointers essentially. And then only the continuation and copy instruction itself has to actually do a memcopy. Yeah, so thank you for your time for coming. So if you want to check out the full paper, which has, you can look at that for more details on the examples, on the semantics, on the type checking, and on proofs of type safety. You can check that out at wasmk.github.io. And also you can download the full implementation based on Wasmtime at wasmk.github.io as well. So thank you for your time, and I'll be happy to take questions that anyone might have.
Thanks, Donald. That was great. And already prompted some interesting conversations. We're at I think the end time. I know you and Arjun said you could stick around a little bit longer. So if people have some questions, we probably can do that. But for those who need to take off, thanks for coming, and see you at the next seminar, hopefully.
Yeah, thank you for the talk.
So I was wondering about the continuation copy. I was imagining that, or assuming, because I'm not really deeply familiar with implementation techniques of languages with multi-shot continuations, that you wouldn't really want to do an ON mem copy. You would want to do some sort of lazy, like frame by frame duplication that would ultimately kind of create a tree. As you return to a frame, then you would lazily clone it or something, which you could do with the nice black box continuation copy instruction. But linear memory shadow stack would be a problem with that, because you would kind of be forced to do that all at once, making me think that if supporting multi-shot continuations was like a serious goal, that one would want a way to kind of semantically be able to lazily copy, as necessary, frame by frame.
Yeah, that's really interesting. Yeah, so to clarify for this work, all we do in this work is we just do a direct memory copy. And yeah, there's definitely different implementation techniques, like you said. So the thing though, if it's separate, so like, how do I say this? So like, I don't necessarily intend like CK itself to be used like directly, right? But the point is that, you know, something like say you want to write some probabilistic programming language, you could compile it to WasmK, right? And if you design your language carefully, you don't have to have a shadow stack, right? Potentially, if you're not doing it in C, right? If you're compiling your own language to WasmK, you don't need to have a shadow stack. And then the continuation copy instruction could still be quite fast using the like more advanced techniques you mentioned. Like I would think. I don't know.
The other thought is that both implementation strategies have trade-offs. And so maybe it suggests that we could look like it'd be worthwhile to consider ways to make it so the application can decide which one is the better one for what it needs. I don't know if we can do that. It's just something that something.
So the other thing I would say is like, you know, for Go, for example, like I believe like they do something with like segmented stacks or something, or excuse me, like growable stacks, right? Where you make a new thread and it starts with a fairly small stack, but then it will like reallocate parts of the stack. Sorry, it will reallocate the stack to grow it as you need to. Right, and you know, of course, that's not possible right now in WebAssembly. That's, you know, hard. But if there's some like more granular ways to manipulate stacks other than, you know, a full copy or something, that's super interesting, right? Yeah.
Does Go do when it grows the stack? Does it do like a memcopy type grow where it just like gets a bigger area and then copies everything, or does it end up with like a linked list of?
I'm trying to like recall because I don't think it's like documented, but I saw this in like a talk from someone on the Go team. And you know, who knows if that's even up to date now anymore. And I think like they actually tried both, and I don't remember which one they settled on.
So they're currently they're doing the equivalent of a mem copy. They take I don't know if they try to realloc the stack or not, but they're going away from segmented stack definitely.
Okay.
And the reason for that is that you get a performance cliff when you're near the end of a segment.
Right.
Hot split problem.
Sorry?
I've heard it called the hot split problem. If you like have a loop that happens to cross it in the middle of the loop, you get unlucky and then it falls off.
Yeah.
Ross, there's this proposal, I think you might have authored it, but about sort of giving direct access to certain kinds of values on the stack. Yeah, I think if one wanted to move forward with any of these ideas, it is worth considering that proposal, which I think allows you to move away from shadow stacks in linear memory. It's worth thinking about how some proposal like that would interact with something along these lines.
You talk about stack inspection.
Yeah, the stack inspection proposal, yes.
Because then you could basically copy your own stack frames as needed.
It would be awesome if stack inspection allowed you to then implement a variety of different strategies like segmented stacks, etc.
Oh, sorry, you can finish.
No, go ahead.
For Lumen, which is an Erlang compiler, right now we need stack switching, so this is great, but probably to actually do that without having to also implement shadow stack, we would need the stack inspection so that we could do the Erlang garbage collection through the Wasm stack.
Yeah.
There's another interesting thought that we had. So what's cool is I didn't realize when I was looking at the paper, I jumped straight to the WasmK part. I skipped over the CK part. And I was thinking like, because Andreas pointed out that C is going to have these problems with these shadow stacks.
Yep.
And so an interesting challenge for like a C module that's say compile a CK is it calls to foreign code calls back. But when it calls back, it doesn't say what shadow stack that C code is using, right? It's just calling back into the module. So the C code then at this boundary will have to do some sort of inspection to say, hey, which shadow stack did you like, was I
Yeah.
calling? And look back and like sort of say, oh, it's that one. Okay, now I know which shadow stack to keep growing and for this call frame.
Yeah. And to be clear, like, yeah, that's independent of Wasm K, right? That's a problem right now, right? You mean, yeah.
We're
Yeah.
stitching things together.
Well, it's not a problem right now because there's no stack switching.
Yeah.
Sure, but if you did the same thing with Go.
Another thought on the earlier topic of which is deleting a stack. We're talking about the problems there. There's also like good reasons why you want to be able to do that, which is if you are a Wasm module trying to run another Wasm module but sandboxed, right? Because then you want to give it, sometimes what you want to do is you want to give it a sandbox function that says, hey, when you call this, just bail out and just, you're done. You've done something bad. I don't want you anymore. You want some way to be like, just leave and don't run any code in this thing anymore because it's done something bad. I think we had an exception handling proposal, something along this. How do you throw a uncatchable exception thing for this? And now, and we were talking, so now I'm realizing these are connected.
Yeah.
So did I understand correctly that your implementation does not copy and restore the C stack, the linear memory stack?
The shadow stack?
Yeah, right.
It does.
Oh, it does. Okay.
Because it has to give the correct semantics in C.
Okay. Cool.
So that's sort of the part that's like that. Well, it was less obvious to me when I started, and it's like sort of the part of the compilation that's like not completely trivial in a sense.
How did you? What kind of code transformation did you need to do for that?
It's more hacks by doing pound defined macros. Yep.
Cool.
Yep.
Actually, I was thinking more about the interleaved native frames. If you have Wasm between, it seems like in any semantics, you would simply not allow suspending a stack that had native frames in the middle. It would just be such a can of worms in any other case. And you could, Wasm spec knows when you leave core Wasm, so it can cut and say, okay, I'm leaving. And then when I re-enter, that's through some, that's also going through a spec path where like I'm entering Wasm from the outside. And that would also kind of delimit a new, base of a continuation such that it was well defined that should, you would cut the stack on both sides, it would seem like, because native code just would not like, it would not do well, especially if we're talking about arbitrary, like host wasn't expecting it code, would not do well with being swapped.
That would have a serious impact on some of my use cases.
Yeah, it would be great for modularity.
Yeah, because you sort of have the case, okay, so some WebAssembly code that you've compiled wants to do threading. Okay, and then what? It just can't do threading if it was called through an FFI chain. I mean, it's reasonable, but yeah, I don't know.
I don't think there's any way
well, so yeah, we need it, and I think the short answer is we need it, because if you do the equivalent of like a global async await where the response is the result of a promise, then you've immediately gone out of you've gone back to JavaScript.
But I think in the meantime, you've exited the stack in a way that's no different than when JavaScript calls into Wasm in the first place. So that's not necessarily
well you're in the middle. You're in the middle. You're in the middle of some. Oh well, you're in the middle of some computation. You do a yield all the way out to the browser loop.
Yeah. Well, that one's fine because it's not interleaving. I mean, there's very few cases where this happens in the browser, like string replace, which takes a Lambda function, is one of the few ones, right? Like it synchronously calls, from JavaScript into native back into JavaScript. And like, there's very few cases like that. It's kind of an anti-pattern, I think.
Well, so I guess the issue is what is native versus what's JavaScript.
That's true, right?
So I guess I can give a little bit more intuition here. So I guess sort of the intuition of our system is that, yeah, you can sort of capture the stack into the table, right? But capturing it doesn't do anything really. All it's doing is just remembering the stack pointer and just saving the stack pointer into the table, right? It's not doing anything more than that in a sort of glib sense, right? And then after this, at this point, you can only talk about new stacks and things that were sort of allocated after the FFI boundary. So yeah, you can do stacks and switching and stuff, but sort of only in the things that were at and beyond that FFI boundary, right? Until you then pop back below the FFI boundary. I don't know if that gives anyone any insights, but that's sort of how I think about it.
So if I'm running some Wasm and then it calls an imported JavaScript function, and then the JavaScript function calls back into Wasm,
Yeah.
and then we try to like save the whole stack, that's not going to work. It's only going to work up to that import call, which is
Well, it's
really
the copy that causes the trouble, really. So if you just stop copying, then we're
Yeah,
good.
I don't know why you wouldn't be able to save that stack. When you save that stack, all you're doing is just saving the stack pointer, right?
Right.
To
So I guess
clarify,
it's copying, right? You can't really copy a JavaScript.
Correct, right, which is what we ban.
I see.
Yeah, so, but Donald, your continuation copy instruction will still work in this scenario, but it'll copy it up to the nearest control delimiter. Correct.
We could have done that, but we didn't.
Oh, it doesn't do that. Oh,
yeah, it doesn't do that. Yeah,
but it could be modified to do that.
It could be modified, conceivably.
The compromise we tried to work through was maybe like, so we thought it'd be bad to be able to copy like other people's stacks because it's just really hard for people to design, like implement their code for that case if they weren't anticipating it. But we made it so that you could copy your own stack or the stack of people who like did sort of sign in to cooperating. And we thought that was like or sort of a compromise that made it so that you couldn't do like mess up people that weren't anticipating it, but still get the people who want to have the functionality able to support it.
Yeah, that makes sense. Feel free whenever anyone wants me to go back to slides, just let me know. I just killed it for now.
Just from industry experience, the way the Beam, the like reference implementation for Erlang does this is once you go to FFI, you can't exit out unless it is completely opt-in, where like the C code knows it's yielding and it actually almost fakes like calling itself again with Erlang terms as arguments. So like it is very much an opt-in. So it's annoying, but like Erlang's used to it. So like we would never have that Wasm to Rust to Wasm again because you couldn't call back into your own memory. You could call back into another Erlang VM, but you couldn't call into the same memory space. So it's not an issue.
Okay, I see.
This would be kind of unfortunate in something like the scripting case where it's really supposed to be well integrated with JavaScript, and you can write the EMASM or EMJS, right, and just have your JavaScript like inline and call it like a normal function. So it's really meant for the case where you have these strongly interleaved frames, and this would make it semantically noticeable whether you implement some function in JavaScript, right, in the embedder as an imported function, or in some other Wasm module as an imported function.
It would also kind of have the side effect of adding stack switching to JavaScript. Like you have the fun effects of I used to try finally, and finally wasn't called, and yet I'm outside of the function now. And it's never called because I never resumed that stack. That's now part of JavaScript, the language, which makes it risky.
I mean, it seems to be the case every time we add something to Wasm, it ends up getting a JavaScript API, and so then JavaScript gets it anyway, even though Wasm is supposed to have cool new features that JavaScript doesn't.
This one is a little weird.
Yeah, this is fundamentally different control flow.
Yeah, so let me jump on something. Let me share the slides again. So about the about returning back. So about returning like back into a try finally, or can you skip it, right? So I guess the intuition here is how can, if you're here in this situation, in what way can you get back to say like the bottom red one, which would let you skip the top red one, right?
Oh,
which is
I'm
probably right.
imagining you suspend it and then never resume it, and you just now from the root of the event
Yes.
loop invoke new code.
Yes. So if you're here and then you just sort of this just stops at like you finish executing here and then you never do anything, right? Well, that kicks in to our case here where it will then call the trap. So that we sort of have this nuclear option right now. So you can't ever sort of, excuse me, you can't ever like finish executing anything that's not a root stack, which is I don't know, strange maybe, but it works, I guess. Yeah.
So what happens already. So finally, clauses in JavaScript even aren't guaranteed because there's certain exceptions that don't run them. Thread aborting doesn't run them. There's certain ways to get.
But only things that are supposed to really kill execution in the whole window. But only that.
And so something we are trying to figure out, because we were trying to figure out how to deal with these like conflicts of sort of needs, and so the model we were trying to work with is, okay, as Donna pointed out, like when you call into somebody, they shouldn't be able to like sort of throw away like everything that's been up to. Like these people are sort of more privileged than you. But if you call down into somebody else, say, hey, you know what? For some reason, I don't like you anymore. You can skip there finally. So it's sort of like whoever is on the outside is more privileged than who's on the inside was the mental model we were trying to work with to figure out how to deal with the conflicts. But we had like, this is why Arjun and Steve, I was bugging you guys security, which I hadn't been able to follow back on. But
it's fun when
Erling,
it's,
Luke, you can go first.
okay. I was going to say it's fun when it's JavaScript because JavaScript can be both on the outside and the inside because it's the same mutable heap.
Yeah.
Erlang has similar things like the finallys where if you trap exits, you're not guaranteed to trap exits because there is a forced shutdown mode where like you are shutting down an whole tree without letting the exit handlers run. So we're fine with that sort of like, it's not guaranteed for finallys.
I feel like this was all a good discussion that is useful. Maybe at this point, we should call it an end. And I'll stop recording.